All right, in this video, we're looking at factoring by grouping. So the first thing we should try to do in factoring a polynomial, of course, is look for greatest common factor. So let's look at our first example here, example A. Is there a GCF for this example? Well, let's just take a look at this last term here, this 8y. The 8y doesn't have anything in common with the 3x to the fifth. So that eliminates any chance of having a greatest common factor. All right, so once we know that there's no GCF, then we're going to look at the number of terms, and we can see that this polynomial has 4 terms. And any polynomial with 4 terms means that we should factor it by grouping, or at least attempt to factor it by grouping. So the normal kind of traditional way to do this is just kind of to group the first 2 terms, and then try grouping the second 2 terms. And oftentimes that's the right answer. So notice here I have the plus sign between the parentheses. I don't want to put the parentheses right next to one another as if they're being multiplied, because that would imply we've already factored it. We haven't done anything yet other than just to associate the terms differently, right? We just put parentheses around them to kind of group them together. Okay, from there, once that's done, then we look for a GCF in each of these parentheses. So I'm going to ask, is there anything in common between these 2 terms that I've put in this first parenthesis? Well, it looks like they certainly have a 3 in common. 3 will go into both of the numbers in the parenthesis, and then certainly x to the 4th can come out of both. So I think I'm going to pull out a 3x to the 4th here. And if I do that, 3 will go into itself once, and x to the 4th will leave just x left over from x to the 5th. So we're just going to have x left standing in that first parenthesis for the first part of it. And then 3 goes into 12 4 times, and x to the 4th will come out entirely, leaving just a 4y left over. So that's what's left in that parenthesis after I pull out my greatest common factor. Now, for the next one, I'm going to actually pull out a 2, because it looks like 2 is common to both of these terms. So if I pull out a 2, of course that'll leave me with x for the first part, and then 2 goes into 8 4 times, leaving me a 4y. And now here's the important part. You can see that this parenthesis and this parenthesis, those 2 binomials are the same. And so if we treat this as essentially one big term, which it is, and this is one big term, we basically have 2 terms that have something in common. So we're going to factor out the parentheses as a GCF. Whenever these parentheses match, like you have them matching here, it means that we can factor that out as a greatest common factor. So the way we factor out this common factor is we basically take that parenthesis that's in common to both terms, we write it out in front, and then we open up a new parenthesis and put the other pieces in that parenthesis. So in other words, if I took out x plus 4y from this, I just have 3x to the 4th left standing. And if I took out that x plus 4y, I'll just have plus 2. And so this becomes your factoring. And you're done. You've now expressed it as a product, and so you're finished. Let's look at example B now. For example B, it's the same thing. We look for a GCF. At this point, I think I do see a GCF that's common to everything. I can certainly pull out an x squared from every term, so I'm going to try that first. I take out an x squared. That'll leave me 3x to the, if I had 7 x's, right, and I take out 2 of them, I'm left with x to the 5th, right, plus 3x to, if I had 5 and I take out 2, I'll have x to the 3rd, plus x to the, if I had 4 and I took out 2, I'll be left with just 2. And then, of course, I'll just have 1 left over after this because I take out all my x's, basically. All right, so there is my leftover expression. The question after that is, can we factor the 4 terms that are in the parentheses any further? I think we can, actually, because it turns out I can group those terms like this. So again, I'm going to create 2 parentheses with a plus sign between them, and I'll group the first 2 first. And then the second 2. All right, so it looks like this parenthesis I can pull out a GCF still. Looks like I can pull out a 3 and an x to the 3rd. So let me write my x squared out here first, and then I'm going to pull out the 3x to the 3rd. Let's see what that leaves us. If we take a 3 out, that'll be gone. X to the 5th, if I take 3 of the x's out, I'll just be left with x squared. Plus, if I took out a 3x to the 3rd, it just leaves me with 1 here. Then I'll have plus x squared plus 1, which there are no GCFs for. But what's nice is that I can see that this parenthesis and this parenthesis are the same. So again, I can then factor that out as a GCF, because there are really what? Just two terms here. This is all multiplied, so it's all one term, and this is the other term. So I have two terms. The greatest common factor for those terms is x squared plus 1. Okay, before I do that, let me just clean up this. I can combine these, right? 3x to the third times x squared is going to give you 3x to the fifth, because you keep the base and add the exponents. And then I'll have my x squared plus 1 plus x squared plus 1. Now I can finish this up by factoring out an x squared plus 1 from both pieces. Now look, if I pull this out, remember I'm going to have a parenthesis to keep all the leftover things. So if I pull that out of the first expression, or first term, I'm left with 3x to the fifth. Then there's a plus sign here, so I'll put plus here. If I pull this out, everything is gone except for there's a 1 that sits in its place, right? Because basically we're dividing. So it's like saying x squared plus 1 divided by x squared plus 1 gives you 1. And this, ultimately, is the solution for problem B. All right, final example, this example C here. Let's give ourselves some room for example C. Okay, looking at example C, if I try to find the greatest common factor, I'll see that 16 really has nothing in common with x squared, for example, so that eliminates any chance of finding something common to every term. The polynomial is 4 terms, so I should try factor by grouping. If I try this first way of grouping, which is the standard way to group the first terms together, and then to group the second terms together, I see that that's not going to work out too well. There's no GCF here at all. It is the difference of squares factoring there, but I don't think that's going to help me, because I don't see how I'm going to end up with an A here. And at that point, the parentheses won't match up, and I won't be able to factor out a greatest common factor at the end. So I think maybe what I'm going to try to do is to group them a little bit differently. So whenever it doesn't look promising, the first grouping, try the next grouping that's available. And sometimes you'll see that that will work a little better. So, for example, what I mean by that is, I'm going to try to pair up the x squared and the 8x. So I'm going to write this as x squared plus 8x first, then minus 16a squared plus 16. And then what I'll do is I'll actually group them as x squared plus 8x plus negative 16a squared plus 16. Okay, now what I've done is, again, just group the first two in a parenthesis and then the last two in a parenthesis. And now I certainly have GCFs. I can pull out an x from the first parenthesis, leaving me x plus 8. And then for the second parenthesis, I can pull out a negative 16. If I do that, I'll get a squared minus 1. Okay, you can see that that doesn't work out too well either. Granted, I could factor a squared minus 1 again as the difference of squares factoring, but then it's kind of hard to see how I can use that. So this is what we would call basically a tough factor by grouping problem. But that's okay, we still have another option. All right, so grouping two terms at a time didn't work. Whenever that happens, we've got to move to a new strategy, and that would be grouping perhaps 3 of the terms together. So I'm going to say that the odd man out is this guy here. This guy with the a squared. I don't really know how that fits in. Nobody else has an a really. So I'm going to push that out and just rewrite this polynomial in the following order. By doing that, it will allow me to group the first piece in a parenthesis and leave the minus 16a squared alone. Now let's take a look what will happen. If I try to factor this trinomial into two binomials, I will have x and x in the first position. 16 will probably factor as 4 and 4. Remember, we always try the closest pair first. And then look, we have a positive sign here, which means basically 2 of that sign on the left. In this case, it'll be 2 pluses. And then I'll have what? X plus 4 times x plus 4. If I check, I can see that that's correct. That'll give me 4x and 4x. Together, that's 8x. And that's the middle term we needed. So we have the middle term, we have the proper factoring. So this is a perfect square trinomial. I can then put that together, right? Summarize it as x plus 4 quantity squared minus 16a squared. And now you may not see this, but you should recognize perhaps that this is a difference, right? And this is something squared, and this is something squared. That means we can break it up, and this is going to be a little complicated looking, but let's do it. We'll break it up into 2 pieces, basically, right? So remember the pattern, it's the root of the first one, so x plus 4 is what's squared, so we just write that down. If you want to put it in parentheses, you're welcome to do that. So I'll do x plus 4 in the front for each one. And then if you remember, the back term here, that gets split up as its root, so it'll be 4a and 4a, right? And then you have a plus and minus sign. That's the rule for difference of squares, right? For example, if you had x squared minus 9, you know that when you split it up, you do x and x because that's the root of the first term split into the front positions. And then 9 becomes 3 and 3 because that's the root of the second term split into the back positions. And then we do plus and minus. Well, we did the same idea here, but we have this complicated expression, right? And then we're done. We've basically factored it. This is a perfectly valid factoring of the polynomial. We have it expressed as a product, and we're good.